In this video, we're going to discuss the generation of plots from these previous data manipulations. So that comes from, E versus effective stress, and also strain, or epsilon versus effective stress. So here's what we can do. I'm going to say we can plot the following. Okay. So one plot we can generate is E versus effective stress with effective stress on an arithmetic scale. Okay. Now, when we say arithmetic scale, we mean not on a log scale. So you just don't set the horizontal axis to a log scale. Okay. Another plot we can generate is E versus effective stress, of course, with effective stress on a log scale. Now, this is the one you're familiar with from CE 322. So I'll put a note here. This is, you should be familiar from CE 322, soil mechanics. That's what we investigated the most back then. We can also plot strain versus sigma prime on an arithmetic scale. And then number 4, we can plot strain versus sigma prime on a log scale. So the only one you're really familiar with from a previous class is plot number 2, but the other 3 are going to be slightly different, okay? Now here's another comment I want to make. When we plot void ratio, so these are the first 2 plots, for these first 2 plots right here, okay, your void ratio plots, we typically display E positive increasing, okay, and I'll show you what that means here in a second. And then for the strain plots, so these 2 right here, we typically display epsilon as positive going down, increasing. Okay, so again, I'll show you, actually I'll just show you right now, okay? So let's look at plot 1, okay? Let's look at plot type number 1. So we would have E increasing up, and here is sigma prime on an arithmetic scale. So this is not on a log scale, okay? So when we generate this data and we plot void, again, this is void ratio here, this is void ratio, we're going to get a shape of a plot that looks something kind of like this, okay? And again, this region right here is our unloading or rebound. So we'll make a little note of this. This right here is unloading, or we sometimes call that rebound. And then here is our loading portion of the curve, okay? Now, what about plot type number 2? Plot 2. So we have void ratio here again, but your horizontal axis, sigma prime, is on a log scale, okay? And so this one, this is again the plot you're kind of familiar with from soil mechanics that looks something like that, okay? And of course, same idea. You got your unloading and loading portions of the curve, okay? And then let's talk about plots 3 and 4, okay? So plots 3 and 4 are these strain plots. And remember here, what was our note? It was saying show strain positive down, okay? And again, the reason why is you have it's a compressive strain. So instead of like calling everything negative and flipping the plot upside down, we just point the positive axis down. And so guess what? You're actually going to get a plot that's very much the same shape as plot 1. So it'll look something like this. So very much the similar type of shape as plot 1. Now, again, the numbers will be different. Why? Because you're plotting strain here. So the numbers are different. And this is, of course, sigma prime on an arithmetic scale again. And then plot 4 here. Here's strain. Here's sigma prime on a log scale. And this plot is actually going to have pretty much the same shape as plot 2, okay? And again, strain is going down, okay? Now here's a note we want to make here, all right? I always say be careful, make a note here, be careful with strain versus percent strain, okay? So if you remember, strain can also be expressed as a percentage, and so you would multiply everything by 100. So I typically use regular strain, which is a decimal, okay? But you could see this data as percent strain. I think in mechanics of materials, we typically express it as decimal strain, but be very careful. If you're gonna deal with strain as a percentage, there should be a percent sign somewhere here. Now, real quick, do you notice anything about this? We'll pause the video and think about it. Think about, do you notice something that you've maybe seen before? Well, these are basically stress-strain plots, especially plots 3 and 4, right? I mean, the only difference is you're reversing the axes, but what do you have? I mean, you have strain versus stress here, okay? The only difference from what you saw in Mech of Materials was we plotted strain on a horizontal axis before, but this is a type of stress-strain relationship, okay? So what information can we get from these plots? Well, let's talk about that, okay? So from these plots, I'm going to say from these plots, we can obtain several soil properties, okay? So let's talk about plot 1, okay? Plot 1, and if you remember plot 1, what was that? Well, that was E versus sigma prime on an arithmetic scale, okay? So the slope of the compression curve, which is the loading curve basically, is the coefficient of compressibility. And we typically call this little a sub v, okay? And little a sub v is equal to negative dE over d sigma prime. And the negative is introduced because you have a decreasing slope. So let's scroll back up here. So if you put a tangent line, at any instant here, you know, at any instant along this curve, you would get a decreasing slope. And so the negative sign indicates you have a decreasing or negative slope there. Now, this is instantaneous, okay? This curvature is highly nonlinear, so you need to get it instantaneously, not, you know, don't put a line through this whole thing, because that's not going to be realistic, okay? So we'll make a note about that. We're going to say, since this curve is highly non-linear, we can approximate a sub v over small pressure increments. Okay, so instead of a differential dE over d sigma prime, we would say A sub v equals negative delta E over delta sigma prime, okay? And then, of course, you can expand this by saying negative E2 minus E1 divided by sigma prime 2 minus sigma prime 1. And again, this negative is the same negative that's out in front here that indicates it's a decreasing curve. And then you can filter that negative through, and you can call that E1 minus E2 divided by sigma prime 2 minus sigma prime 1 over some kind of small pressure increment, okay? So let's go to plot number 2. Plot number 2 is which of the following? Plot 2 is, let's see, E versus effective stress on a log scale, okay? Yep. I'm just going to scroll down here. Plot 2 is E versus effective stress on a log scale, all right? So this one's the one you're familiar with, right? Basically what we say is the slope of the virgin compression curve is called the compression index. And this is, again, what you're familiar with. We call this C sub C, okay? So this is the slope of the, I'm not going to call it linear, I'll say, you know, straight portion of the curve. All right, so we'll say C sub C equals negative D sub E over D log effective stress. And again, the negative indicates a decreasing slope. So we can, you know, express this as a delta. We could say C sub C equals negative delta E over delta log effective stress, and this should be familiar to you. And so of course we get negative, you know, E2 minus that's not a sigma, E2 minus E1 divided by log sigma prime 2 minus log sigma prime 1, okay? And then you know, we can rewrite this as C sub C equals E1 minus E2, and then we can, you know, collapse these logs, because when you subtract the difference of two logs is the log of the quotient, so sigma prime 2 divided by sigma prime 1, okay? And this should be a familiar formula to you. We you know, covered compression index extensively when we were in soil mechanics, and of course, you know, we can put a note here, the slope of the rebound curve is the swell index, C sub S. You may remember that, okay? What about plot 3? We got 2 more to go. Hang in there. What about plot 3? Plot 3 was, that shouldn't, it's not sigma prime. I don't know. We got some extra marks in here. So plot 3 is strain plotted against sigma on an arithmetic scale, okay? So we're talking about plot 3 now, so let's scroll on down. Just going to go to another page here. Plot 3 is strain versus sigma prime on an arithmetic scale. All right. And so what do we get from this? Well, the slope of the compression curve is called the coefficient of volume change. Coefficient of volume change. And we call this M sub V. And so M sub V is going to be d epsilon d sigma prime. Now notice there's no negative here. Well, that's because we plotted epsilon as positive downwards, and so that takes care of the change of sign. That takes care of the sense of decreasing versus increasing data. Okay, so we can express this in delta form: delta epsilon over delta sigma prime. Okay, and it turns out that the coefficient of volume change is also equal to A sub V over 1 plus E naught, which you can relate this to your void ratio plot, okay? So this is it pretty much. And then another way to express this, we can say M sub V is equal to 1 over capital D, where D is a special term called the constrained modulus. Okay, and then let's go to the fourth plot. The last plot is going to be the following. Let's just scroll down to the next page. Plot 4 is strain versus sigma prime, and sigma prime is on a log scale. Okay, so the slope of the compression curve is called the modified compression index. Okay, and we call this C sub C epsilon. So this is a lot like C sub C, okay? And we can say C sub C epsilon is equal to, delta epsilon divided by log sigma prime 2 over sigma prime 1. So similar to what we saw with plot 2, similar in form to plot 2, okay? And so this is going to be epsilon 2 minus epsilon 1 divided by log sigma prime 2 divided by sigma prime 1. Again, notice there's no negative lingering out in front here because we've reversed the direction of the positive epsilon axis, okay? So we can also say C sub C epsilon equals C sub C over 1 plus E naught, okay? So there are definitely some advantages of using epsilon versus log effective stress data. So let's talk about those real quickly. There's some advantages of using epsilon versus log effective stress data, okay? This is easier to estimate field settlement. So this is an advantage over using void ratio. I mean, if you got strain instead of void ratio, then you can calculate settlements much more easily because, again, it's strain now, right? Also there is, you can get data, you can obtain and plot data in real time more easily compared to the void ratio data. Okay, so that's pretty much it. And this is kind of a long video, so maybe take a second and absorb this and look over these things. But these are the 4 different kinds of plots we can generate from either void ratio versus effective stress or strain versus effective stress and their accompanying properties.